The wind cut different across the open plains of northern Dakota Territory. Jack M. learned that his first winter of 1875, when his above-ground cooking fire inside the lean-to shelter flickered and died 3 times in one gale, forcing him to burn through nearly 2 cords of wood in a single week just to keep the camp pots boiling. He had built his fire exactly the way every trapper across the territory was told to build it. Standard log fire ring, lean-to windbreak, stack the cordwood and tend it manually, trusted and proven. By midwinter, the wind was consuming double the fuel, while smoke backed into the shelter and cooking took twice as long. Across the northern plains, trap camps were fighting the same losing battle with above-ground fires that failed when the wind howled hardest. Over the next 3 seasons, Jack quietly applied techniques borrowed from a Sioux guide and his German father to build an underground fire chamber that cooked with half the wood and stayed steady in 40-mile-per-hour gusts. His fellow trappers called it excessive digging until the big storm hit and their fires failed while his kept cooking. In this video, I'll break down the exact dimensions, the hidden airflow principle, and the step-by-step construction that made this underground system outperform every standard campfire. What did Jack understand about wind and flame that every other trapper in the territory had missed? Jack M. had spent his early years learning trap lines from scouts who worked the Missouri River tributaries, men who measured winter survival by how much cordwood they could haul and how long their fires stayed lit when the prairie wind turned vicious. By 1875, at 28 years old, he was running cook duties for a 12-man winter camp near what would become Bismarck, responsible for keeping 3 8-quart cast iron pots boiling daily and maintaining the camp's main cooking fire through months when temperatures dropped to 20 below zero Fahrenheit. The standard method had been passed down through every trapper manual and quartermaster guide Jack had ever seen. Build your fire ring with logs set in a square, stack split cordwood in neat piles outside the lean-to shelter, maintain a stone chimney or open draft, and feed the flame manually as needed. The assumption was simple. The northern Dakota Territory had abundant timber in the coulees and river breaks, so fuel economy mattered less than keeping the fire accessible and visible for camp warmth. Most trap camp supervisors allocated 3 to 4 cords of split wood per winter season for cooking alone, plus additional cordwood for heating the shelters. What the manuals never addressed was what happened when sustained winds above 30 miles per hour hit the exposed prairie camps for days at a time. Jack discovered this gap in the wisdom during a January storm that lasted 4 consecutive days, with gusts that rattled the lean-to walls and sent snow swirling horizontally across the camp clearing. The stone chimney he had built according to standard specifications began pulling backward, drawing cold air down into the fire, instead of creating the upward draft that was supposed to carry smoke away from the cooking area. Flame temperature dropped noticeably, and the wood that should have burned clean began smoldering, producing thick smoke that filled the lean-to shelter and forced the campmen to cook with wet cloth over their faces. Even worse, the open sides of the lean-to, designed to provide cross-ventilation in calm weather, became wind tunnels that buffeted the flames from multiple directions. Jack watched his carefully stacked cordwood disappear at nearly double the normal rate, not because the fire was burning hotter, but because the wind was stealing heat faster than the wood could replace it. The cooking pots, which normally reached a full boil within 40 minutes, took over an hour and 20 minutes to heat water for the evening stew. By the 3rd day of the storm, Jack calculated that his camp was burning through wood at a rate that would exhaust their winter supply by early March, leaving them with no cooking fuel for the final 6 weeks of the trap season. The failure extended beyond fuel consumption. The erratic flame made temperature control impossible, causing the bottom of the stew pots to scorch, while the top remained lukewarm. Cast iron pot handles, normally safe to grab with a leather glove, became too hot to touch safely as the irregular flame licked up the sides unpredictably. Twice during the storm, sudden wind shifts blew burning embers out of the fire ring and onto the stack of split cordwood, requiring men to leave their cooking duties to prevent the fuel supply from catching fire. Tom H., the camp foreman who supervised 3 similar winter operations across the region, visited Jack's camp on the 4th day of the storm and dismissed any suggestion that the standard method was inadequate. Standing in the smoky lean-to, squinting against the backdraft, Tom insisted that the solution was simply more wood and a bigger fire. He had seen camps weather worse storms by doubling their cordwood allocation and assigning extra men to tend the flames around the clock. The idea of changing a proven system seemed not just unnecessary, but wasteful of labor that could be spent on trap line maintenance. Jack had different teachers. His knowledge came from three sources that most trappers either ignored or never encountered. The first was a Sioux guide named Running Wolf who had worked with Jack's scouting parties in the early 1870s, before the heavy settlement pushed most of the Dakota bands further west. Running Wolf had shown Jack how Plains winter hunters dug shallow fire pits on the lee side of hills and used the natural wind patterns to create steady combustion even in open country. The technique was practical, not ceremonial, designed for hunters who carried limited fuel and needed reliable heat in exposed terrain. The second source was Jack's own father, a German immigrant named Heinrich who had worked as a woodfeller and sawmill foreman in Pennsylvania before moving west. Heinrich understood ventilation from managing mill furnaces and had taught Jack that controlling airflow was more important than controlling fuel volume. He had built stone-lined hearths that used half the wood of conventional fireplaces by directing draft through carefully sized channels, principles he had learned in the Black Forest region where fuel was expensive and winters were long. The third teacher was Jack's own record keeping. Unlike most camp cooks who estimated fuel usage, Jack maintained a daily log of cordwood consumed, cooking times, and flame behavior under different weather conditions. 3 seasons of data had shown him that wind was the single greatest enemy of cooking efficiency, wasting more fuel than cold temperature, wet wood, or poor chimney design combined. As the January storm finally broke, Jack made a decision that would set him apart from every other camp cook in the territory. Instead of accepting higher fuel costs and longer cooking times as inevitable consequences of prairie wind, he would test whether the underground fire techniques Running Wolf had demonstrated could be adapted to a permanent winter camp cooking system. He understood that he was challenging more than just a preferred method. He was questioning the fundamental assumption that above-ground fires were inherently superior to any alternative. The experiment would require him to dig, to dirty his hands with earthwork that most trappers considered beneath the dignity of a camp cook, and to risk the mockery of men like Tom H., who trusted only in methods that looked familiar and required no learning of new principles. 2 weeks after the storm passed, Jack began his site survey with the systematic approach his father had taught him for laying out mill operations. The camp occupied a natural clearing in a coulee that provided some shelter from the worst prairie winds. But Jack had learned that conventional wisdom about wind protection was backwards. Most camp supervisors chose the most sheltered spots they could find, reasoning that less wind meant easier fire management. Jack now understood that eliminating wind entirely also eliminated the natural draft that could make an underground system work efficiently. The prevailing wind in the region came from the northwest during winter months, carrying Arctic air across hundreds of miles of open prairie before hitting the Missouri River breaks. Jack spent 3 days observing how this wind behaved around the camp's terrain features, noting that the natural draw of the coulee actually accelerated airflow in certain spots while creating dead air pockets in others. He marked locations with wooden stakes, measuring wind speed at ground level using a simple cloth strip method his father had shown him for testing mill ventilation. Running Wolf's technique had been designed for temporary hunting camps where mobility mattered more than permanence, but the core principle could be adapted to a fixed winter camp. The Sioux method involved digging the fire chamber into the lee side of a slope or ridge, then positioning the air intake tunnel to face directly into the prevailing wind. This created a natural bellows effect where wind pressure forced fresh air through the intake tunnel into the fire chamber, while the rising hot gases escaped through a separate opening. Jack selected a spot 15 feet southeast of the main lean-to shelter, where the natural slope of the coulee would allow him to dig the fire chamber slightly below grade while keeping the intake tunnel entrance above the typical snow accumulation level. The location provided protection from the worst crosswinds while ensuring that the northwest winter winds would blow directly into his intake system. This positioning also kept the underground fire close enough to the shelter for practical cooking work, while preventing smoke or heat from interfering with sleeping areas. The excavation began in early February, when the ground was frozen but still workable with proper tools. Jack dug the main fire chamber first, creating a circular pit 18 inches in diameter and 10 inches deep. The size was calculated based on his largest cooking pot, allowing enough space around an 8-quart cast iron vessel for heat circulation, while keeping the chamber small enough to concentrate flame effectively. Heinrich's mill experience had taught Jack that chamber size directly affected combustion efficiency. Too large and heat dispersed uselessly. Too small and airflow became restricted. The critical innovation came in positioning the intake tunnel. Rather than digging it horizontally into the side of the fire chamber, Jack angled it downward from the surface toward the bottom of the fire pit, creating a slope of roughly 30 degrees. This downward angle served two purposes. It prevented snow and debris from settling in the tunnel during storms, and it directed incoming air underneath the fire, forcing it upward through the fuel for more complete combustion. Heinrich had used similar principles in furnace design, understanding that air entering below the burning material created better heat transfer than air entering at flame level. The intake tunnel itself measured 4 inches in diameter and extended 3 feet from the chamber to its surface opening. Jack carved it carefully with a narrow trenching shovel, maintaining consistent dimensions to avoid airflow bottlenecks that would reduce draft efficiency. The tunnel emerged at ground level 36 inches northwest of the fire chamber, positioned to catch the prevailing wind at an angle that would maximize air pressure without creating turbulence. Within the first week of testing, Jack discovered a fundamental flaw in his initial design. During a moderate snowstorm, wind-driven snow accumulated around the intake opening, gradually blocking airflow and causing the fire to burn poorly. The problem became worse when the snow melted during the day and refroze at night, creating an ice plug that completely sealed the tunnel entrance. Jack had anticipated debris issues, but underestimated how quickly prairie snow could accumulate around ground-level openings. His solution combined practical field observation with Heinrich's mill yard experience. Jack built a low earthen berm around the intake opening, roughly horseshoe-shaped and 8 inches high, designed to deflect wind-borne snow while maintaining airflow into the tunnel. The berm's shape created a wind shadow on the lee side of the intake, allowing snow to settle away from the opening while preserving the wind pressure that drove the draft system. The second refinement addressed a problem Jack had not anticipated. Small debris, dry grass, bark fragments, and ice crystals were being drawn into the intake tunnel by the strong draft, occasionally clogging the narrow passage and reducing airflow. Jack fabricated a simple wooden grate from thin strips of oak, creating a barrier with gaps large enough to allow air passage, but small enough to block most debris. The grate fit snugly into the intake opening and could be removed for cleaning when necessary. Testing the complete system required careful measurement of fuel consumption and cooking performance under various wind conditions. Jack established a controlled comparison by cooking identical meals using both his underground system and a conventional above-ground fire on alternate days, maintaining detailed records of wood usage, cooking times, and flame behavior. Over a 3-week period in February, with winds averaging 20 to 30 miles per hour and temperatures ranging from -5 to -20 degrees Fahrenheit, the results showed clear differences. The underground system consistently used approximately 30% less cordwood for the same cooking tasks. More significantly, cooking times remained stable regardless of wind conditions, while the above-ground comparison fire required 40 to 60% longer to complete identical tasks when winds exceeded 25 miles per hour. The underground fire also produced remarkably little visible smoke, making it nearly undetectable from a distance of more than 50 yards. The positioning strategy proved equally important as the construction technique. Jack tested alternate locations around the camp and discovered that placing the system too close to natural windbreaks actually reduced its efficiency, while positioning it in areas with moderate wind exposure improved performance. The optimal location balanced wind access for draft with protection from the most extreme gusts that could overwhelm the system's capacity. After confirming the basic efficiency gains of his positioned chamber system, Jack encountered a heat loss problem that no Frontier manual had ever addressed. Despite the superior draft and wind protection, his underground fire was consuming more fuel than his calculations predicted during the coldest periods of late February. The issue became apparent when he measured the chamber walls with his bare hand during cooking sessions. The earth surrounding the fire pit felt cold to the touch, even after an hour of steady burning, indicating that precious heat was flowing directly into the frozen ground instead of staying concentrated around the cooking vessels. Heinrich's mill furnace experience had taught Jack that any fire system was only as efficient as its ability to contain and direct heat energy. In Pennsylvania sawmill operations, furnaces lined with uninsulated brick or stone wasted enormous amounts of fuel because the masonry absorbed heat into its mass and conducted it away from the combustion zone. The same principle was now working against Jack's underground chamber, where the Dakota Territory's permanently frozen subsoil was acting as an infinite heat sink, drawing thermal energy away from the fire faster than the burning wood could replace it. Running Wolf had addressed this problem in temporary hunting camps by using the natural insulation properties of snow and prairie sod. During their scouting expeditions, Jack had observed the Sioux guide packing loose snow around the exterior walls of his fire pits, creating an insulating barrier that prevented heat loss while remaining easy to remove when breaking camp. For permanent winter positions, Running Wolf had shown Jack how plains hunters used a different technique. They excavated sod in rectangular blocks and stacked these grass side inward around the fire chamber walls, creating both insulation and thermal mass that would absorb heat during active burning and radiate it back into the chamber during fuel-adding periods. Jack began experimenting with thermal mass in early March, when the ground had thawed enough to make digging easier, but temperatures still dropped well below freezing each night. He excavated additional space around his existing fire chamber, creating a ring of loose earth approximately 6 inches wide, extending outward from the original walls. Into this space, he packed alternating layers of prairie sod and loose soil, building up the insulation to ground level and extending it 2 inches above the chamber rim to prevent heat loss through the top edges. The sod provided the crucial element that plain earth lacked. The dense root systems and organic matter created thousands of tiny air pockets that trapped heat, while the decomposing grass generated a small amount of additional thermal energy through natural composting processes. Jack discovered this effect by accident when he noticed that the sod-packed areas around his fire chamber remained noticeably warmer to the touch than areas insulated with plain soil, even several hours after. The fire had died down. Heinrich's influence appeared in Jack's approach to the chamber floor and walls. German furnace design emphasized creating barriers between the fire and any materials that would conduct heat away from the combustion zone. Jack applied this principle by excavating an additional 4 inches of depth from his fire chamber floor, then filling this space with a foundation layer of fist-sized stones collected from the creek bed. This stone foundation served 2 purposes. It provided drainage for any moisture that might seep into the chamber, and it created an air gap between the burning fuel and the cold earth below. The wall treatment required more sophisticated technique. Jack lined the interior walls of his fire chamber with a mixture of local clay and chopped prairie grass, applied in a layer roughly 1 inch thick. The clay came from deposits along the Missouri River tributaries, a gray-blue material that hardened when dried, but retained enough flexibility to expand and contract with temperature changes without cracking. The grass fibers, cut to lengths of 2 to 3 inches, served as reinforcing material that prevented the clay from splitting when exposed to the intense heat of burning wood. This clay lining created a reflective surface that directed radiant heat back toward the center of the chamber, instead of allowing it to be absorbed into the surrounding earth. The smooth, light-colored interior also made it easier to gauge fire intensity by observing flame color and behavior, something that had been difficult with the original rough earth walls that absorbed light and created misleading shadows. The most significant innovation involved elevating the actual fire base above the chamber floor. Jack placed 2 flat limestone slabs, each roughly 8 inches square and 2 inches thick, directly on top of the stone foundation layer. These slabs created a raised platform that lifted the burning fuel completely away from contact with cold surfaces, while providing a stable, level base for consistent combustion. The airspace beneath the slabs allowed heat circulation while preventing the cooling effect that occurred when burning wood rested directly against cold stone or earth. Testing the enhanced system required precise measurement of fuel consumption under controlled conditions. Jack conducted a 2-week comparative trial in mid-March, using identical cooking tasks and maintaining detailed records of wood usage, fire duration, and thermal performance. Each day he prepared the same menu: morning coffee and oatmeal for 12 men, midday soup, and evening stew with cornbread. He measured cordwood consumption by counting split pieces of standardized size, each approximately 18 inches long and 4 inches in diameter. The results exceeded his expectations. The insulated and lined chamber used approximately half a cord of wood during the 2-week test period, compared to 3/4 of a cord required by his original uninsulated underground system for identical cooking tasks. More importantly, the enhanced chamber maintained cooking temperatures much longer after fuel additions, reducing the frequency of wood feeding from every 20 minutes to every 45 minutes during active cooking periods. The thermal mass effect became apparent during extended cooking sessions. The sod insulation and clay lining absorbed heat during peak burning periods, then released this stored energy gradually as the active flames diminished. This created a more consistent cooking temperature that prevented the feast or famine heat cycles that plagued both above-ground fires and his original underground chamber. Pots of stew that previously required constant stirring to prevent scorching now cooked evenly with minimal attention. The chamber walls, when tested with bare hands during cooking operations, now remained warm to the touch rather than cold, indicating that heat was being retained within the system rather than conducted away into the frozen ground. The clay lining showed no signs of cracking or deterioration after 2 weeks of daily use, suggesting that the grass fiber reinforcement was successfully managing thermal expansion stresses. Jack also discovered an unexpected benefit of the insulation system during fuel shortages. When cordwood supplies ran low due to delayed deliveries, the enhanced chamber's heat retention allowed him to stretch limited fuel over longer cooking periods without sacrificing meal quality or safety. With his insulated chamber system proven effective at fuel conservation, Jack faced a more complex engineering challenge that became apparent during his daily cooking routine. The enhanced underground fire produced excellent combustion and retained heat efficiently, but the actual transfer of that heat energy to his cooking vessels remained inefficient. His 8-quart cast iron pot, when placed directly over the fire chamber opening, created a bottleneck that prevented proper flame circulation and resulted in uneven heating patterns that scorched food while leaving other portions undercooked. The problem manifested most clearly during stew preparation, where consistent heat distribution was crucial for proper cooking. Jack observed that flames from his underground fire shot straight upward in a narrow column, heating only the center bottom of his pot while leaving the outer edges relatively cool. This created hot spots that burned ingredients in direct contact with the pot bottom while barely warming food near the edges. The issue worsened when he attempted to cook multiple items simultaneously, as placing 2 pots over the chamber opening blocked airflow and caused the fire to burn poorly. Running Wolf's traditional cooking method addressed heat distribution through a technique that most frontier cooks had never encountered. Plains hunters used flat sandstone slabs as cooking surfaces, positioning these stones directly over their fire pits to create an even heating platform. The stone absorbed heat from flames below and distributed it evenly across its surface, eliminating hot spots while providing a stable work area for multiple cooking vessels. Jack had observed this technique during their scouting expeditions, but had not understood its engineering advantages until he faced similar heat distribution problems in his own system. The stone platform solution required careful material selection and precise sizing. Jack located suitable sandstone slabs along the creek beds, choosing pieces that were flat, roughly 20 inches square, and approximately 3 inches thick. The thickness was critical. Thinner stones cracked under thermal stress, while thicker pieces took too long to heat evenly and wasted fuel. He tested several specimens by subjecting them to rapid heating and cooling cycles, selecting only stones that showed no signs of fracturing or flaking under temperature stress. Installation of the cooking platform revealed the importance of proper support structure. Jack discovered that placing the stone slab directly over his chamber opening created dangerous instability, as the slab could shift or tilt when pots were moved, potentially causing accidents with boiling liquids. He solved this by building a permanent stone ring around the chamber perimeter using smaller rocks mortared with clay, creating a stable foundation that supported the cooking slab while maintaining access to the fire chamber below for fuel additions and maintenance. Heinrich's forge experience provided the critical insight for optimizing flame circulation around cooking vessels. German metalworking forges used carefully controlled airflow to direct flame around the workpiece rather than allowing it to escape unused. Jack applied this principle by modifying his intake tunnel configuration to create more controlled combustion patterns. He reduced the intake tunnel diameter from 4 inches to 3 inches, which increased air velocity entering the chamber and created more turbulent mixing of fuel and oxygen. The smaller intake diameter had an unexpected consequence that initially appeared to be a design flaw. The higher velocity airflow created a more intense but smaller flame that concentrated heat in an even smaller area beneath cooking vessels. However, Jack discovered that by extending his intake tunnel length from 3 feet to 4.5 feet, he could slow the incoming air just enough to create a more distributed flame pattern while maintaining the combustion intensity needed for efficient cooking. The breakthrough came when Jack realized that flame pattern could be controlled by modifying the chamber interior geometry. He placed a curved piece of limestone, roughly the size of his fist, at the point where the intake tunnel entered the fire chamber. This deflector stone forced incoming air to change direction abruptly, creating turbulence that spread the flame laterally, rather than allowing it to shoot straight upward. The result was a flame pattern that wrapped around the bottom and lower sides of cooking vessels, dramatically improving heat transfer efficiency. Testing this flame deflection system required systematic measurement of cooking performance under controlled conditions. Jack prepared identical batches of venison stew using both his original straight flame configuration and the modified deflector system, measuring cooking times, fuel consumption, and food quality. The deflector configuration reduced cooking time for a full pot of stew from 45 minutes to 28 minutes, while using approximately 20% less cordwood. The improvement in heat transfer efficiency created an unexpected safety benefit. With flames spreading laterally rather than shooting directly upward, the cooking slab surface remained at more manageable temperatures, reducing the risk of severe burns when handling pots or adjusting their positions. The distributed flame also eliminated the extreme temperature gradients that had caused his cast iron handles to become dangerously hot, while pot contents remained lukewarm. Jack refined the system further by experimenting with cooking vessel positioning. He discovered that elevating pots approximately 2 inches above the stone cooking platform using simple iron legs allowed heated air to circulate completely around the vessel bottom and lower sides. This created an oven-like effect where hot gases were trapped momentarily around the pot before escaping, maximizing heat transfer while maintaining the benefits of the stone platform for even heating. The elevated cooking position also simplified fuel management. Jack could add cordwood to the fire chamber without removing cooking vessels, as the raised pots provided adequate clearance for fuel insertion through the chamber opening. This eliminated the cooling cycles that occurred when pots had to be moved during extended cooking sessions, maintaining more consistent temperatures and reducing total cooking times. By late March, Jack's refined cooking chamber system demonstrated measurable superiority over conventional methods in every practical metric that mattered to winter camp operations. Cooking times were reduced by an average of 35%, fuel consumption decreased by nearly half, and food quality improved due to more even heating patterns that prevented scorching while ensuring thorough cooking. The system also proved remarkably tolerant of different cooking vessel sizes and shapes, accommodating everything from small coffee pots to large soup kettles without requiring design modifications. The stone cooking platform showed remarkable durability, maintaining its structural integrity and heating properties after weeks of daily thermal cycling between fire temperatures and ambient cold. The ultimate test of Jack's integrated underground cooking system came during the winter of 1881, when a massive Arctic storm system stalled over the northern Dakota Territory for 7 consecutive days. The blizzard brought sustained winds averaging 45 miles per hour, with gusts exceeding 60 miles per hour, temperatures that dropped to 35 degrees below zero Fahrenheit, and snowfall that accumulated in drifts reaching 6 feet in sheltered areas. Weather conditions of this severity occurred perhaps once every decade in the region, creating survival challenges that separated proven systems from inadequate ones. Jack's camp faced the storm with a carefully managed fuel supply that reflected 3 seasons of experience with his underground system. His winter cordwood allocation totaled 2½ cords of split oak and ash stored in a covered lean-to shelter adjacent to the cooking area. This fuel load was 60% smaller than the 4-cord standard recommended by territorial quartermasters for camps of similar size, a reduction that Jack felt confident making based on his documented fuel efficiency gains from previous winters. 3 neighboring trap camps within a 5-mile radius provided natural comparison subjects for testing system performance under identical weather conditions. Tom H's operation maintained the standard above-ground cooking fires with stone chimneys and lean-to windbreaks, following territorial quartermaster specifications precisely. Reed S.'s camp used a variation of the conventional method with larger fuel allocations and double-walled shelter construction around the cooking area. The third camp, supervised by a French-Canadian trapper named Dubois, employed a hybrid approach using both above-ground fires and a crude underground pit for emergency backup cooking. The storm's intensity became apparent on the second day when Tom H's main cooking fire began experiencing severe draft problems that conventional solutions could not address. His stone chimney, built according to standard territorial specifications, created a backdraft effect when wind speeds exceeded 35 miles per hour, forcing smoke and partially burned gases back into the cooking shelter. The camp's crew attempted to solve the problem by rebuilding the chimney with additional height and installing improvised wind deflectors around the shelter opening, but these modifications provided only temporary relief. By the third day, fuel consumption at Tom H's camp had increased to nearly double the normal winter rate. The combination of backdraft problems and wind-disrupted combustion meant that cooking fires burned inefficiently, producing less usable heat per unit of cordwood while requiring constant attention to maintain adequate flame intensity. Simple tasks like boiling water for coffee required 45 minutes instead of the typical 20 minutes, and preparing the daily stew for 12 men stretched to nearly 3 hours of active fire tending. Reed S.'s camp fared somewhat better due to heavier initial fuel allocations and an improved shelter construction, but still experienced significant operational difficulties. His double-walled cooking area provided better wind protection than Tom H's setup, but the improved shelter also restricted airflow needed for proper combustion. Reed's crew solved this by opening gaps in the shelter walls to improve draft, which eliminated the wind protection and returned them to essentially the same problems faced by conventional setups. The most revealing comparison involved actual fuel consumption measurements. Jack maintained precise daily records of cordwood usage during the storm, counting split pieces and weighing representative samples to calculate total fuel mass consumed. His underground system used approximately 3/4 of a cord during the 7-day storm period, maintaining normal cooking schedules and meal quality throughout the entire event. Tom H's camp consumed nearly 2 full cords during the same period, while Reed S.'s operation used 1 3/4 cords, despite reducing meal frequency and accepting longer cooking times. More significant than fuel efficiency was the operational reliability difference between systems. Jack's underground chamber continued functioning normally throughout the storm, requiring only routine fuel additions and standard maintenance procedures. The intake tunnel remained clear due to his berm and grate modifications, and the insulated chamber walls maintained consistent temperatures that supported predictable cooking times regardless of external wind conditions. The conventional camps experienced multiple operational failures that compromised both safety and nutrition. Tom H's crew suffered 2 incidents of smoke inhalation when backdraft conditions overwhelmed their shelter ventilation, forcing them to cook outdoors in sub-zero temperatures while wearing wet cloth face coverings. Reed S.'s camp lost an entire day's food preparation when wind-scattered embers ignited stored cordwood, requiring men to abandon cooking duties to prevent a larger fire that could have destroyed their entire winter fuel supply. On the 6th day of the storm, when fuel shortages at neighboring camps became critical, Tom H. and Reed S. visited Jack's operation to observe his cooking system firsthand. Jack demonstrated the underground chamber's performance by preparing a full meal for 15 men, including visitors, using standard fuel loads, and maintaining normal cooking schedules. The demonstration showed not only the system's efficiency, but also its operational simplicity under extreme conditions. The visitors examined every aspect of Jack's installation, measuring chamber dimensions, testing the stability of the cooking platform, and observing flame behavior through the complete cooking process. Tom H., whose skepticism had been legendary among regional trap camp supervisors, acknowledged that the underground system delivered measurable advantages that conventional methods could not match. Reed S. requested detailed construction specifications and began planning to modify his camp's cooking area before the following winter season. The storm's aftermath revealed the broader implications of the performance differences. Jack's camp emerged from the 7-day ordeal with adequate fuel reserves remaining and no weather-related equipment damage or safety incidents. The neighboring camps faced shortened winter seasons due to excessive fuel consumption, reduced nutritional quality from meals that could not be properly prepared, and equipment losses that would require replacement during the spring resupply period. Word of Jack's system's performance spread through the regional trapper network during the spring trading gatherings. Camp supervisors from across the Northern Territory sought information about construction techniques and operational procedures, leading to widespread adoption of modified underground cooking systems throughout the region. By 1885, territorial quartermaster manuals included specifications for wind-resistant underground cooking installations, formally recognizing techniques that had previously been dismissed as primitive or impractical. The technical principles that Jack had integrated into his system became standard knowledge among professional outdoorsmen and homesteaders throughout the Northern Plains region. Military expedition reports from the 1880s reference underground cooking chambers as preferred methods for extended winter operations in exposed terrain. Homestead construction guides published in the early 20th century devoted entire chapters to underground fire systems, acknowledging their superiority for fuel. Scarce regions where conventional heating and cooking methods proved inadequate. Modern survival instruction and bushcraft education recognize the Dakota fire pit technique as among the most efficient field cooking methods for windy conditions, validating principles that Running Wolf had taught and Jack had systematically refined through methodical experimentation and precise measurement.